Alright guys, welcome back to another Algebra 2 online lesson. As we concluded nonlinear systems of equations with the last target, we are now starting a new unit. So again, we're currently not having a unit test. If we do get back to school at some point in time, we will work to get tests in, but for right now, we are going to go ahead and start the next unit. The next unit is all about sequences and series, and so this is something that we are going to start off with, basically covering the basis of what a sequence is and what a series is. In Algebra 1, you looked at definitely sequences, and I believe series as well, and so some of this is going to be review, but we want to make sure that we nail some of the key points down and are very efficient in understanding and finding terms in sequences and series in order to progress with what we're going to get into a little bit more in-depth content. So let's start with some definitions. If the first section you have here, if you printed out the notes and you want to follow along, those notes are on Google Classroom. If you don't have a printer available to you, that's okay. Take some good notes on a sheet of paper, and you will be able to use those again for your assessment at the end of this target. So the first section here is finding the terms of a sequence given the general term or basically a description of what the sequence is. And so in order to find terms, we need to understand what a sequence is. So a sequence is basically a list of numbers in a specified order. Order is important for sequences. So for example, you see some numbers on the screen, 3, 5, 7, 9. You may notice that these are odd numbers and that they are increasing. And so the order is definitely that they're an increasing set of numbers. And so this would be a sequence. This is what we would actually call a finite sequence. This would be a finite sequence because it does end. So it stops at 9. So we would say that this again is finite. Now, sequences can go on forever. So basically how we would represent this in general terms is instead of writing this as 359, if we wanted to represent this as a potential sequence that could be any values, this is one specific sequence, but we can write that with what we often show as like an a sub 1 for the first term, a sub 2 for the second term, a sub 3 for the third term, and a sub 4 for the fourth term. And you could keep going on and on. So as I have this listed right here, this would be a finite sequence as well. A sub 1 would represent 3, a sub 2, 5, a sub 3 would represent 7, and a sub 4 would represent 9. Now, if I wanted to, or if we needed to, we could continue this with basically 3 dots. And so you see this in algebra, or sorry, you see this in English, meaning that this is going to continue. So this would actually, if we write it in this format, this would be an infinite series, meaning those dot dot dot, that those 3 points, meaning that it goes on forever and ever. Now, this may go on for more than just 4 terms, but may end. And so how we would represent that would be to have those 3 dots there to represent that there's some continuing pattern. So there's a 1 term, 2 terms, 3 terms, 4 terms, and then there's some more terms. And then a sub n would be a place that it would stop. And so this, again, right here, if it's written in this format, would be finite as well, because it's going to stop at a sub n, whatever a sub n is. Okay, so this is the general description for a sequence of any kind. In problem number 1, we get to a specific sequence, but it's not written out as numbers or terms, it's written as an expression, and we have to find the terms. So in problem 1, it says, for the sequence shown below, find a sub 1, a sub n, and a sub 6. So basically what this description here means is n is the number term. So like we saw up above in the definition, a sub 1 is the first term, a sub 2 is the second term, sorry, a sub 3 the third term, and so on and so forth. So a sub n could be any term in the order. So what this is asking us is to find a sub 1. A sub 1 would be the first term in the order. So what we can do there is we can write this as a sub 1 and then substitute in a 1 for the n's. So this would end up being 1 plus 1 over 1 squared, and 1 plus 1 over 1 squared would be 2 over 1, which is 2. So the first term, a sub 1, would be 2 in this sequence. If we wanted to find the second term, we would write this as a sub 2, which would be 2 plus 1 over 2 squared. 2 plus 1 is 3. 2 squared is 4. So this would be 3 over 4. And we could continue on with this pattern to find a sub 3, a sub 4, so on and so forth. It actually wanted us to go ahead and jump now and find a sub 6, so the sixth term. So go ahead and see if you can pause the video for a moment and find that sixth term. Hopefully you were able to find that sixth term, and to do so we would find a sub 6, which is replacing n with 6, so 6 plus 1 over 6 squared. 6 plus 1 is 7, and 6 squared is 36, which does not reduce. So this would be 7 over 36. That's our sixth term. So these would be 3 of the terms in the sequence. Now, we don't know if this sequence is infinite or if it's finite. It doesn't really tell us, but we know that there's at least 6 because we're trying to find 6. If you wanted to find the terms in between, you could find those as well. Let's go ahead and take a look at another example. Problem number 2. In problem number 2, the expression is a little bit different here. So the expression is a sub n equals negative 1 to the nth power times 2 to the nth power. So we could write that as, in this example, it wanted us to find the first 4 terms of the sequence. So the first term would be a sub n, which would be negative 1 to the first power times 2 to the first power. And we could do this in our calculator if we needed to, but negative 1 to the first power times 2 to the first power is just negative 1 times 2, which is negative 2. To find the second term in the sequence, we would do the same thing here and replace n with 2's. So in this one, you may need to type this into your calculator, that's okay. Negative 1 to the second power times 2 to the second power would be, I'm mistaken how I typed this in. There we go. Would be positive 4. Then a sub 3, which would be the third term, would be negative 1 to the third power times 2 to the third power. Again, you could type that into your calculator, negative 1 to the third times 2 to the third, and that gives us negative 8. Now, if you see the pattern here, you may be able to find the fourth term. If we look at the terms, this goes negative 2, 4, negative 8. You might assume the next term is going to be a positive 16. And if you typed that in or substituted in the n value as 4, you would find out that it is a positive 16. And so the first 4 terms are negative 2, 4, negative 8, and 16. So if we wanted to list this as a sequence, we could say that the first, we could write this out in ascending order here with value, but noticing that it does change from positive to negative and alternating items here. So negative 2, 4, negative 8, positive 16. You might take a guess that the next number would be negative 32, and then positive 64, and then so on. So if this were to be a finite series and we only wanted 4 terms, sorry, a finite sequence and we only wanted 4 terms, here's our 4 terms. But maybe this is an infinite sequence. If this were the case, we could represent that by putting these 3 dots, meaning that you'd continue this pattern. So we can find terms in a sequence by substituting in for the n value for whatever term we're looking for. So 1 for the first term, 2 for the second term, 10 for the 10th term, 100 for the 100th term, so on and so forth. You can also find terms that by figuring out a pattern that's occurring in the sequence and continuing that pattern along. So this is the basic definition for a sequence. So let's go ahead and move a little bit more in depth and take a look at what we actually call recursive sequences, and something that can be used in sequences called factorial notation or factorial. So a recursive sequence is basically a sequence that is determined by using the previous terms. So each term is set up by using the term that came before. So in problem number 3, it says write out the first 8 terms of the recursive sequence defined by C of n, where C of 1 equals 1 and C of 2 equals 1. And this is actually known as the Fibonacci sequence. It's, in terms of mathematics, one of the most famous sequences that exist. But we're going to take a look at this from an algebraic standpoint. Just finding terms. So the first 8 terms. So C of n is equal to C of n minus 1 plus C of n minus 2. So this notation here means, remember that the n is the number of the term. So basically what this saying is C of n is determined by the term that came before it added to the term that came 2 times before it. So for example, the 5th term is determined by taking the 4th term and adding it to the 3rd term. So we want to find the first 8 terms. It gives us the first one, the C of 1, and the second one is also 1. So if we want to find the third one, C sub 3 is found by taking C sub n minus 1, which is C sub 2, plus C sub n minus 2, which would be C sub 1. So C sub 2 is 1, and C sub 1 is 1. So if I take 1 and I add it to 1, that's 2. So C sub 3 is 2. Do the same thing to continue finding terms. So C sub 4 would be C sub 4 minus 1, which is C sub 3, plus C sub 4 minus 2, which is C sub 2. So basically the 2 successive terms that came before are added together. C of 3 we just found is 2. C of 2 it gave us initially was 1. So 2 plus 1 is 3. So C of 4, the 4th term, is 3. We can continue again. C of 5. So C of 5 would be the 4th term added to the 3rd term. Our 4th term we found was 3. Our 3rd term we found was 2. So 3 plus 2 is 5. And we can continue this pattern. So see if you can find terms 6, 7, and 8 using this same general idea. So go ahead and pause the video, find terms for the 6th term, the 7th term, and the 8th term. Okay, so hopefully you were able to find those. Oops, sorry. So the 6th term would be found by taking the 5th term and adding it to the 4th term. So the 5th term was 5, 4th term was 3, so 5 plus 3 is 8. Then the 7th term would be found by taking the 6th term and adding it to the 5th term. The 6th term was 8, the 5th term was 5, and so 8 plus 5 is 13. And finally, the 8th term would be taking the 7th one and adding it to the 6th one. So 13 plus 8 is 21. And so the first 8 terms here for the Fibonacci sequence would be 1, 1 that they gave us, then 2, 3, 5, 8, 13, 21. Now we could actually continue this pattern. So this one is actually an infinite sequence because it could go on in the same pattern. But we were only expected to find the first 8 terms. So there's the first 8 terms. If you want to put the 3 points there to show that it continues, you could throw those then at the finish. So this would be an example again of a recursive sequence where it used previous terms denoted by this n minus 1 and n minus 2 to show us that this is one term before and this is two terms before to come up with our new term. Now, the other relatively new thing that we get here is what we call factorials. So you may have seen this in Algebra 1, but you may not have seen this in Algebra 1. So factorials basically have a algebraic type expression for them. So basically for any natural number n exclamation point, this is what we call n factorial. So when you see that exclamation point in math, it means factorial. N factorial basically means to multiply every integer starting with n and going down to 1. So that's what this expression means right here. So n times the n minus 1 times n minus 2 all the way down to n times 3 times n times 2 times n times 1. So for example, if I had, let's say, 6 factorial. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. 10 factorial would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So whatever number is being factorialed, if you will, I don't know if that's a term, but whatever number we're taking the factorial of, we take that number and multiply it with every successive integer decreasing all the way to 1. Now, we can use that to evaluate expressions, but we can also make things a little bit easier on ourselves if we understand how to simplify some expressions. So I'll show you how to evaluate factorials in the calculator here in a little bit. But let's say we have 9 factorial over 7 factorial. In problem number 4, it says simplify each of the following by writing the numerator in an equivalent form. So I could rewrite the numerator for A as 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But I could actually write it a little bit shorter. So I could write this as 9 times 8 times 7 all the way down to 1. 7 all the way down to 1 can be represented as 7 factorial. Well, why did I choose to stop at 7 factorial? Well, if you take a look at the denominator, what we may notice here is that the denominator is 7 factorial. So if I wrote this all out, so let me go ahead and just do this very briefly. If I wrote this all out, 7, 6, 5, 4, 3, 2, 1, all over 7, 6, 5, 4, 3, 2, 1. What we'd see here is a lot of terms would cancel each other out. So instead of writing all that out, what I can do is write this as 7 factorial, or stop the numerator at 7 factorial, and then cancel out 7 factorials. So now what that leaves me with is 9 times 8. And if we do 9 times 8, that is 72. So 9 factorial over 7 factorial, many different ways to come up with this answer, but we can do this pretty quickly by changing 9 factorial into 9 times 8 times 7 on down to 1 with 7 factorial, and then canceling out the 7 factorials. Let's take a look at a similar way to do b. So we have 11 factorial over 8 factorial times 2 factorial. Now we could multiply out this denominator, multiply out this numerator, and then simplify, but a quicker way is again to write the numerator, break that numerator up into 11 times 10 times 9 times 8 factorial. And then over the denominator of 8 factorial and 2 factorial. So I stopped at 8 factorial because now the 8 factorials cancel out. Now, there's not a way to simplify this really any further. So what I'm going to do here is I'm going to pull out the graphing calculator. I'm going to use the graphing calculator to help us get this answer. So the numerator is 11 times 10 times 9, which some of you may be able to do in your head, which is okay. It's 990. The denominator is 2 factorial, which remember 2 factorial just means 2 times successive numbers down to 1. So just 2 times 1. So basically this number is 990 over 2. And So I can divide that in my calculator and get 495. Now, see if you can do something similar to solve for C, or to evaluate for C. So pause the video, try to simplify the expression, and then use that to evaluate for C. Hopefully you were able to come up with an answer here. So in the numerator, I could start writing this down as 6 times 5 all the way down, but what I may do here is I may stop at 5. Because 6 times 5 factorial, 5 factorial would mean, again, I'm going from 5 all the way down to 1, is a simplified version of the numerator, and what I can do now is cancel out the 5 factorials. So this is now 6 over 3 factorial. Now, what some of you may wrote this out as 6 over 3 times 2 times 1, which would be 6 over 6. That would be perfectly okay to write this. 6 over 6, and then this would simplify down to 1. Now, you can do a little bit of a shortcut using your graphing calculator. So if I hit the graphing calculator here, and I want to do 6 over 3 factorial, I can do 6 divided by. Now, there's a few different ways to find the factorial button. So I can hit 3, and then one way to find the factorial button is to hit the math key and go over here to probability. And there it is down as the fourth option. So hit you math and then go over to PRB, which is probability. It's the fourth option down. So then I can have that input right there. And now I have 6 divided by 3 factorial. And in my calculator, this actually simplifies without that extra step. So it does show us that it's 1. So in this case, we did have to simplify the numerator and then get the answer. But I also could have used the calculator to just do C. So let me take a look at the top here. If I go 6, and then I can find that factorial button by going to math, probability, down to this fourth option. Then I can do in parentheses for the denominator, so divided by 3 factorial times 5 factorial, which is the expression we see here. Hit enter, and it gives me 1. So because this tells us to simplify the numerator, we can do that to simplify the factorials and get a value, or we can just type this into the calculator. Okay, so basically the goal here is kind of figuring out what factorials mean, and that means to take a number and multiply it by every successive integer until you get all the way down to 1. Now let's go ahead and take a look at some sequences that actually use factorials. So if we go ahead and take a look at problem number 5, in problem number 5 it says find the third term of each sequence listed below. So there's a number of terms in the sequences. We're just going to practice using these sequences defined by factorials by just finding the third term. So the third term for A would be A sub 3, which means we can substitute in 3 for n. So this would be 3 factorial over 2 to the third power. So once we do the substitution, again, this is the third term, so 3 is for n. We substitute in for 3, or 3 in for n. Once we do the substitution, we can evaluate this expression. Now, you could simplify if you wanted to simplify, but let's just go ahead and use the calculator. So I'm going to hit 3 factorial divided by, and then in parentheses for the denominator, I'm going to do 2 to the third power. And there we have the answer. So if you want to leave this as 0.75, you can. This would also be known as 3/4. So simplifying the numerator, 3 factorial would be 3 times 2 times 1, which is 6. 2 to the third would be 8. You don't necessarily need to show this step, but then it would simplify to 3/4. Same thing goes for C. In C, we want to find the third, or sorry, B. In B, we want to find the third term for this listed sequence. The sequence is a little bit more complicated as we have numerous values for n, and it's in different locations, but it's the same concept. So C to the third, or sorry, C sub 3 means that we substitute in 3 for n. So this would be negative 1 to the third power times 2 times 3 minus 1 inside of parentheses, then a factorial all over 3 factorial. So now let's simplify this. Negative 1 to the third power is just negative 1, so I'm just going to leave a negative in front of the parentheses. 2 times 3 minus 1 would be 6 minus 1, which is 5. So this would end up being negative 5 factorial. Notice the factorial here is going to be taken of the 5, and then we're going to take the opposite, the negative of that. And then this is over 3 factorial. So if I wanted to simplify this by hand, I could. I could do this as negative 5 times 4 times 3 factorial, all over 3 factorial. And notice that the 3 factorials cancel out, and that gives me negative 20, or negative 5 times 4, which is negative 20. So you could do this by hand. You could also take this step right here once we simplified and do that in the graphing calculator. So you could type in negative 5 and then factorial, and then divided by 3 factorial. And there we have the value, negative 20. So factorials can be used in sequences as well. Again, that factorial just means take that number and multiply it by every successive number as you reduce to 1. Now let's move a little bit more in depth or further into the concept of sequences in series and take a look at what a series is. So in order to talk about series, we probably need to know the definition of a series. So a series is essentially the sum of all terms in a sequence. So if we find a sequence, the ordered description of numbers, and we add up all those points together, that gives us the series. So let's say we're given a sequence, and this sequence is some value a sub 1, a sub 2, a sub 3, and it goes all the way up to a sub n. So it's finite, and it has these terms. We don't know what the terms are, but those are the terms. If we wanted to find the series, then we would take the first term, add it to the second term, add it to the third term, and continue doing that process all the way until we get to the very last term. So for example, let's take a look at 6. 6 says given the sequence, given this sequence a of n equals 2 times n, find the value of s sub 4 and s sub 7. So s sub 4 and s sub 7 basically tells us we want to find the value for the series. So if I want to find s sub 4, basically what s sub 4 means to do is take a sub 1, add it to a sub 2, add it to a sub 3, and add that to a sub 4. So we want to add up all those terms. So I can find those terms by taking 1 and substituting it in for a sub n. So a sub 1 would be 2 times 1, which is just 2. A sub 2 would be 2 times 2, which is 4. A sub 3 would be 3 times 2, which is 6. And a sub 4 would be 2 times 4, which is 8. And so if I wanted to find the series for the first 4 terms, s sub 4, that would be 2 plus 4 plus 6 plus 8, which is 20. So s sub 4, the series for the first 4 terms, is 20. See if you can find s sub 7, or the series for the first 7 terms of a sub n. So pause the video now. Okay, let's check our answers. So s sub 7, following the same concept, is a sub 1, the first term, plus a sub 2, the second term, plus a sub 3, the third term. And you can continue doing that all the way until you get to the 7th term. So a sub 1 we already found was 2, a sub 2 we found is 4, a sub 3 is 6, a sub 4 is 8. If you wanted to find a sub 5, you could either follow this pattern you see that's occurring here, that they're all even numbers, successive even numbers, or you could do 5 times 2, which is 10. A sub 6 would be 12, and a sub 7 would be 14. And then if you added all those numbers together, you should get 56. So the series for the first 7 terms of that sequence is 56, adding all those terms together. Now there's some notation that represents this concept, and it's what we call summation or sigma notation. So if we have a series for n, and I'm going to write this out instead of type this in. actually. This is what we call summation notation, or sigma notation. So S of n, remember this is the series. So the series for the n number of terms. Here we see this sigma. Basically, the sigma means to add, or to find the series of. The k down here at the bottom, this is what we call k equals 1. This is what we call the lower limit, or the term at which we begin adding. The n up top is what we call the upper limit, or the term at which we end. We stop adding. A sub k is known as a few different things, but we can call it the element, and this is basically the formula for finding the terms. So this summation notation basically tells us to do what we did here. It's just written differently. So if I wanted to do the summation notation for this part, it would have been, for S of 4, it would have been k equals 1 at the bottom because we started at the first term, 4 at the top because we ended at the fourth term, and then 2n would have been my value here, or actually 2k, since k is the variable shown there on the bottom. So let's take a look at an example. Now this is the same notation, it's just shown a little bit differently. The word editor changes the location, but this is basically the 4 is on top, the I equals 1 is the bottom. So I is not imaginary here, it's just a variable. So this is saying find the series for 3i plus 2, starting with the first term and going all the way to the fourth term. So we can basically rewrite this. And I'm not going to show all the work because that's a lot of writing, but we can basically rewrite this as finding a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. That's what this means. So if I want to find the summation, I need to add each one of these terms together. So I can use my calculator if I need to. 3, actually I don't need to on the first one, shouldn't need to maybe at all, but if you need to, you can. So the I for the first term is 1, so 3 times 1 is 3 plus 2 is 5, so my first term is 5. My second term, the I would be 2, so 3 times 2 is 6 plus 2 is 8. My third term, the I would be 3, so 3 times 3 is 9 plus 2 is 11. And my fourth term, if I see the pattern here, would be 14. You could also take 4 times 3, which is 4, plus 2 is 14. Now I want to add all of these together here, so the following sum is 38. So summation notation is basically what we did on the page before. It's just written a little bit differently. Let's look at, actually, let's go ahead and, if you get the idea, go ahead and pause the video and see if you can do B.